We are all accustomed to thinking of solutions as mixtures of a substance dissolved in water. But in fact, the meaning of the term solution is broader than that. Perfumes, antiperspirants, the air we breathe, the alloys we come across in daily life like steel, brass and bronze are all solutions. The utility or importance of solution in life depends on their composition. Body fluids are examples of complex liquid solutions containing many different solutes like electrolytes, sugar, urea, oxygen and carbon dioxide. The importance of the concentration of solutions can be seen from the fact that any change in their concentration can have a significant impact on the living system. For example, 1 part per million or 1 ppm of fluoride ions in water prevent tooth decay, while a concentration of 1.5 ppm causes spotted tooth. And any concentration at and above 4 ppm becomes toxic. Therefore, sodium fluoride is used as rat poison. Intravenous injections are always dissolved in water containing salts at particular ionic concentrations, so as to match the blood plasma concentration. A solution is defined as a homogeneous mixture of two or more chemically non-reacting substances whose composition can be varied within certain limits. A homogeneous mixture is one in which the composition and properties are uniform throughout. In a solution, the component that is present in a smaller quantity is known as the solute or the dissolved substance. The component that is present in a larger quantity is known as the solvent or the dissolving substance. The solution has the same physical state as the solvent. A solution containing only one dissolved solute in a solvent is called a binary solution. Depending upon the physical state of the solvent, various types of solutions that can be formed are a solution in which a gas is the solvent, and a gas, a liquid, or a solid is the solute, is known as a gaseous solution. For example, air is an example of gas in gas type of solution. Chloroform mixed with nitrogen gas is an example of liquid in gas type of solution, while camphor in nitrogen gas is an example of solid in gas type of solution. A solution in which a liquid is the solvent and a gas, a liquid or a solid is the solute is called a liquid solution. Oxygen dissolved in water is an example of gas in liquid type of solution. Ethanol dissolved in water is an example of liquid and liquid type of solution, while glucose dissolved in water is an example of solid in liquid type of solution. These liquid solutions occupy a special place in chemistry, as most chemical reactions take place in solution phase. Similarly, a solution in which a solid is the solvent and a gas, a liquid, or a solid is the solute is called a solid solution. A solution of hydrogen in palladium is an example of gas in solid type of solution. An amalgam of mercury with sodium is an example of liquid and solid type of solution, while copper dissolved in gold is an example of solid in solid type of solution. Out of the various types of solutions we just discussed, the most significant are those that are in the liquid phase. We will therefore confine our study to binary liquid solutions. The concentration of a solution is defined as the amount of solute present in a known amount of solvent or solution. Concentration can be expressed qualitatively as well as quantitatively. Qualitatively, we describe a solution as either dilute or concentrated. When a solution contains a small proportion of solute relative to the solvent, we call it a dilute solution. On the other hand, a concentrated solution contains a large proportion of solute relative to the solvent. This qualitative means of describing concentration, although useful, sometimes leads to confusion, and thus arose the need for a quantitative description of solutions. Quantitatively, the concentration of a solution can be described in several ways. These methods are mass percentage, volume percentage, mass by volume percentage, parts per million, mole fraction, molarity, molality. Let's discuss these methods one by one. Let us first discuss the mass percentage or weight by weight percent method. The mass percentage of a component of a solution is defined as the mass of the component in the solution divided by the total mass of the solution multiplied by 100. It is important to note that as we are expressing the concentration in percentage, it implies that we are defining it per 100 units of the solution. If X grams of component A is dissolved in Y grams of component B, then the mass percentage of A is given by X, which is the mass of A divided by X plus Y, which is the total mass of the solution multiplied by 100. For example, a 20% weight by weight solution of sodium chloride in water means that 20 grams of sodium chloride is present in 100 grams of the solution. Note here that 80 grams of water and 20 grams of sodium chloride make 100 grams of the solution. Another way of expressing concentration in percent is volume percentage or volume by volume percent. The volume percentage of a component in a solution is defined as the volume of the component divided by the total volume of the solution multiplied by 100. The concentration of solutions, where both the solute and the solvent are liquids, is commonly expressed using this method. For example, 25% of ethanol solution in water means 25 milliliter of ethanol is dissolved in 75 milliliter of water, such that the total volume of the solution is 100 ml. Yet another way of expressing concentration in percent is mass by volume percentage. This is expressed as the mass of the solute divided by the total volume of the solution multiplied by 100. For example, a solution of 23% weight by volume contains 23 grams of solute per 100 milliliters of the solution. This way of expressing concentration is widely used in medicine and pharmacy. When a solute present in a solution is in a very small quantity or trace amounts, then its concentration is expressed in another quantity known as parts per million or ppm. Parts per million or ppm is defined as the ratio of parts of the solute to million parts of the solution. Mathematically, It is expressed as the total parts of the component divided by the total number of parts of all the components of the solution multiplied by 10 to the power 6. The concentration can be expressed as mass to mass, volume to volume, or mass to volume. For example, the concentration of dissolved oxygen in seawater is 5.8 grams per 10 to the power 6 grams of seawater and is written as 5.8 ppm. Also, the concentration of pollutants in water or the atmosphere is often expressed in terms of ppm. Now let us discuss another commonly used concentration term, the mole fraction. The mole fraction of a component in a solution is defined as the ratio of the number of moles of that component to the total number of moles of all components in the solution. It is represented by X. Mole fraction is an ideal way of representing the concentrations of various chemical species in a mixture. It is useful for representing concentrations in gaseous mixtures. For example, in a binary mixture, if the number of moles of A and B are Na and Nb, respectively, then the mole fraction of A, Xa, equals Na divided by Na plus Nb, and the mole fraction of B, Xb, equals Nb divided by Na plus Nb. It can be seen that the sum of the mole fractions of component A and component B is 1. That is, Xa plus Xb equals 1. In a solution containing I components, the mole fraction of the ith component, Xi, is expressed as Ni divided by N1 plus N2 plus N3 and so on. It is important to note that the sum of the mole fractions of all the components of a solution is always equal to 1. That is, in a solution of I components, X1 plus X2 plus X3 and so on till Xi is equal to 1. For example, if a solution contains 4 moles of alcohol and 6 moles of water, then the mole fraction of alcohol can be calculated by substituting the values of the number of moles of alcohol and the number of moles of water in the formula. Thus, mole fraction of alcohol equals 4 divided by 4 plus 6, which is equal to 0.4. As the sum of the mole fractions of all the components of a solution is always equal to 1, the sum of the mole fraction of alcohol and the mole fraction of water is 1. Or, the mole fraction of water is 1 minus 0.4 or 0.6. Noted here that mole fraction is a dimensionless quantity. Let us now look at another frequently used concentration term, molarity. Molarity is defined as the number of moles of a solute dissolved in 1 liter of the solution. It is represented by capital M. Mathematically, the molarity of a solution can be represented as M is equal to N. The number of moles of solute divided by V, the total volume of the solution in liters. If Wb grams of the solute of molar mass Mb is present in V milliliters of a given solution, then M is equal to Wb divided by molar mass Mb multiplied by 1000 by V ml. Now let us solve a numerical problem on molarity. Calculate the molarity of a solution containing 10 grams of sodium hydroxide in 500 ml of the solution. The first step is to write the formula for molarity. Then, list the given variables. That is, Wb is equal to 10 grams, V is equal to 500 ml, molar mass M for sodium hydroxide is 40 grams per mole. Now, substituting the values in the formula and solving it, we get M is equal to 0.5 moles per liter. Another very important method of expressing the concentration of a solution is molality. It is represented by small m. Molality is defined as the number of moles of a solute dissolved per kilogram of solvent. Mathematically, it is represented as m is equal to n, the number of moles of the solute divided by the mass of the solvent in kg. If Wb grams of the solute is dissolved in Wa grams of the solvent, then the expression for molality becomes m is equal to Wb divided by the molar mass of the solute multiplied by 1000 by Wa. Let us solve a numerical problem based on molarity and molality. An antifreeze solution is prepared from 222.6 grams of ethylene glycol, C2H6O2, and 200 grams of water. Calculate the molality of the solution. If the density of the solution is 1.072 grams per milliliter, then what will be the molarity of the solution? The first step is to list the given variables. Wb is equal to 222.6 grams. Wa is equal to 200 grams. And the density of the solution is 1.072 grams per milliliter. The molar mass of ethylene glycol is 62 grams. Substituting these values in the formula for molality, we get M is equal to 222.6 divided by 62 multiplied by 1000 by 200. On solving, we get M is equal to 17.95 moles per kg. Next, let us find the molarity of this solution. You will have to calculate the volume of the solution since molarity takes that into account. The total mass of the solution is the sum of the mass of ethylene glycol and the mass of water. That is, 222.6 grams plus 200 grams, which is equal to 422.6 grams. Using the value of density of the solution, which is 1.072 grams per milliliter, you can calculate the volume of the solution. Density is equal to mass per unit volume, and thus V is equal to 422.6 grams divided by 1.072 grams per milliliter, or V is equal to 394.2 milliliter. Now substitute this value of V in the expression for molarity. Therefore, M is equal to 222.6 divided by 62 multiplied by 1000 divided by 394.2. On solving, we get M is equal to 9.1 moles per liter. Each method of expressing the concentration of solutions has its own merits and demerits. Mass by mass percentage, parts per million, mole fraction, and molality are independent of temperature, whereas molarity, volume by volume percentage, and mass by volume percentage are functions of temperature. This is because volume is a temperature-dependent quantity, while mass is independent of temperature. Solubility